Okay, so let's look at an interesting method that will allow us to be able to create what's called zero knowledge proofs. And the method that we'll look at is what's called accumulators. So for this we have zero knowledge proof. So with accumulators, it's all about defining that we have a single data element which can be published that contains individual data elements, and where we can make a commitment to all of the data elements in here, but not actually reveal them. And then when required, we can actually prove knowledge to any one of the data elements without revealing the other elements within the accumulator. So we'll look at two different methods to be able to do this. And the first is elliptic curve cryptography. And the second is RSA. So there are two ways that we can implement these accumulators. Elliptic curve, which is probably the most preferred in terms of efficient processing, and RSA based on existing RSA type methods. So with elliptic curve cryptography, what we have is that we have an elliptic curve, might look a bit like that, where we have an equation such as this, mod of P. And this gives us this type of shape. And we have values for A, we have a value for B, and P is the prime number. When we bring in the prime number, we create what's called a finite field, and these become little dots speckled across X and Y. And they become integer values for the X and Y values. But we also get an order, and the order is the number of points in which we can operate with for the curve. Along with this, we have a base point on the curve called G. So what we do is that we create a secret key value, which is a scalar. Typically it's a 256-bit random number. And we select our curve. So let's say we'll pick the curve that's used in Bitcoin and Ethereum as Sept256K1. That has a standard base point on the curve, and the equation that we have is this, mod of P. So this becomes our curve, and then what we do is that we select a secret key value. This becomes what's called a scalar. We then multiply our base point by the scalar to give us our public key value here. And this is a point on the elliptic curve here. And basically it's G added SK times. And we have a very, very efficient way of doing that with inside elliptic curve. So elliptic curve tends to be fast in computing these values here. Okay, so that's the main parameters that we have. We have our curve and our base point, and we can create a public key value. So we start off and we create our secret key value, which becomes our private key. And we keep this secret. Then we create our public key, which is equal to SK times G. So the public key is a point on the elliptic curve. SK is our scalar value for a private key. So this becomes a 512-bit public key because it's an X and a Y. And this becomes a 256-bit secret key value. This is our base point. So then we take our data. So let's say we have our data. And we take a hash of it. So So typically this is a 256-bit hash of the data. And we now want to add that data onto our accumulator. So with an accumulator, what we do is we start off with a 0 value, and then we add on a data element, and it creates another accumulator value, and then we can keep adding our values onto the accumulator, and it changes the value. We can then create a proof of knowledge to be able to prove that we know one of those values, and if Bob is sending to Alice, then we can create a commitment to the accumulator, and then we can create a proof of knowledge of knowing one of the values within inside the accumulator, and Alice can check that. We can also delete a value from the accumulator at any time, and then we will be able to change the values that are stored within the accumulator. So when we delete this value, when we try to create a proof of knowledge towards that, it won't actually work. So we start off with the base point for the accumulator. So we initialize to the base point on this curve here. Then when we add a new value, y1, we take y1, which is just a scalar value, 256 bits, and we add on the secret key to give us this scalar value here. We then take the existing point, and we calculate a new point on the elliptic curve as this one. This becomes a public value, and we can display the accumulator value to anyone. And then what we can do is we can provide a proof of knowing y1 to whoever wants it. But we need our secret key to be able to update the accumulator, but our public key can then be used to prove the existence of a value. When we now want to add on a new value, y2, which is the hash of data 2, we take that and we add on our secret key, and then we multiply by a1 to give this. So we basically multiply each time to give us a new accumulator value. If we now want to remove the value of y1 to give us a new accumulator value, we basically divide by y1 plus sk. Take our hash again and create y1 again. We want to get rid of this value from the accumulator. We basically divide our current accumulator by that. So with this, we can then create a proof. So after we have this, so because this is A2 is that times that times that, so we'll end up with this value times that value here. So when we create a proof of knowledge of y2 in this case, we will get a true. When we create a proof of knowledge of y1 from our accumulator value here, we will get a false value. And the way that this is actually done with inside elliptic curve is that we take the value of y1 plus sk, and we take an inverse mod of O in this case. Okay, and again, it's a very efficient operation. Take this value, we do an inverse mod of the order, and we'll end up getting this value. We can then multiply that value by the accumulator value to give us our new accumulator value. Okay, so this is the way that we do our elliptic curve. We typically use big integers because we're using 256-bit values here, and that's much greater than our normal 64-bit integer values. So now let's look at the RSA method for this. So with this, we will start off having 4 data elements, D1, D2, D3, D4. Just like before, we will take a hash of those, and then from that hash we'll create the seed of a random prime number. So we end up with 4 prime numbers in this case, P1 to P4. After this, what we do is that we will keep our secret, and our secret is the multiplication of each of those 4 prime numbers. We'll then define a modulus as we would normally do in RSA by taking 2 prime numbers and multiplying them together. So typically this might be 1000 bits, 1024, 1024, so we create a 2048-bit modulus here. We then create a commitment by generating a random value, a generator here, and it's somewhere between 1 and n minus 1. And we raise that to the power of s, and we take mod of n. So the value of n can be public, the value of g can be public, but the value of s is secret in this case. So this becomes our accumulator value, and we can make it our commitment to knowing D1, D2, D3 and D4. Now we want to show that we know P3 and P4, but we want to keep P1 and P2 secret. So for that, we'll compute a value of R for P3 times P4, and we'll create a value of U equal to P1 times P2. So this becomes the secret value, and this is the value that we want to show from our commitment. So if we've maybe been asked for these 2 data elements, and we can reveal them without revealing the rest of the data inside the accumulator. Okay, so we have U and P there. So we now create our new proof by taking G and raising it to the power of U mod of n. So it shouldn't be possible to discover the value of U knowing P, G and n there. After that, we can now, if we send this proof to Alice, say, then Alice can then take this proof and raise it to the power of R. So R is the value here of the 2 values that we're revealing that we actually know. So we send R and we send P, and Alice is now able to prove the knowledge of those values. So the P becomes G to the power of U here. That's G because of logs, G to the power of U to the power of R becomes UR. And U times R is equal to S. So that becomes S, and obviously this is all done mod n. So we can now check, Alice can now check that the value ties up with the value that she received in there. So again, we can see that it is possible for Bob, this is Bob, to provide knowledge to Alice, have a commitment here as the accumulator, and then to be able to send over the R value, the values that he's revealing without revealing P1 and P2, then the P value. Alice takes that value, raises it to the power of that value, takes mod n, and then we'll end up with this value here. So in this way, Bob has actually revealed some of the values that he has without actually revealing the other values. And that's the power of accumulators, where we can define zero knowledge proofs, and we can prove things that data exists without actually revealing other data. Thank you.